What if someone whispered to you that the most elaborate surveillance act in the history of the cosmos is unfolding this very moment, and the unsuspecting subject under the lens is us? It sounds like the premise of a science fiction epic, yet the sky itself seems to be staging such a drama. Every few years, without fail, something ancient and uninvited slips out from the abyss between the stars and brushes past our solar neighborhood. In just 8 short years, 3 such wanderers have arrived, an extraordinary rhythm, almost like a celestial heartbeat. The latest of these, known as 3-1 Atlas, was first detected on the first day of July in the year 2025, streaking through space along a hyperbolic orbit, moving so swiftly that even the gravitational hold of our sun could not tether it. It was here, and then it would be gone, its trajectory pointing not to return, but to glide onward into eternity. Most of the world never noticed when this emissary entered our vicinity, but those who did look closely saw something that gnawed at the imagination. Its path did not resemble a careless accident of celestial mechanics. Its timing, arriving in cadence with its predecessors, seemed too sharp to dismiss as chance. The suggestion hung unspoken in the data. Perhaps we are not watching stones from the void, but rather keeping appointments with them. And so the story unfolds, carried on the wings of mathematics and orbital mechanics, numbers that whisper of impossibilities and hint at designs beyond mere chaos. Could these be scouts? Emissaries dispatched across the gulf of interstellar night, transmitting silent reports back to masters hidden far beyond our comprehension. It is a question that chills even as it fascinates, a riddle that pulls science into the domain of myth. For now, we can only trace their arcs across the heavens, watching as they slice through the dark like cryptic signatures in the sky. What might they be searching for? And what happens if they succeed? As we settle into this exploration, we find ourselves not just gazing at comets or asteroids, but staring into the possibility of an intelligence that regards us the way we might observe ants on the ground, curiously, distantly, perhaps with purpose unknown. Each streak of light above us might no longer be random, but a signpost in an unfolding cosmic drama. And if that is true, then humanity's story may already be entwined with forces vast enough to change the way we understand our place in the universe. An object from the space between the stars entered our neighborhood, and almost no one thought to look up. On the first day of July in the year 2025, astronomers working at the Atlas Survey Facility in Rio Hurtado, Chile, captured evidence of something that by all traditional understanding of the solar system should not have been there. It was moving at a velocity of 137,000 miles per hour, a speed no object bound by the gravity of our sun could ever sustain. This interloper, named 3-1 Atlas, was not following the familiar loops of ellipses or circles. Its trajectory was hyperbolic, a mathematical fingerprint with only one interpretation. This visitor had come from elsewhere, from the cold and unlit regions between the stars, and its path assured that it would never return. The mathematics admit no mercy. When you chart the speed of a body against its distance from the sun, those bound within our star's gravity well draw graceful, predictable arcs. Asteroids, comets, even the icy wanderers of the distant Kuiper belt all perform this familiar dance, slowing as they climb away from the sun's grasp and quickening as they descend back toward it. This is orbital mechanics in its purest form, the basic law that has governed celestial motions for billions of years. Yet 3-1 Atlas refuses to join the choreography. Its path is that of a runaway, unbound, tearing through space on a course that cannot be retraced. When it swings closest to our star, on the 30th day of October in the year 2025, it will whip around like a stone released from a sling, borrowing momentum from the Sun itself before hurling back into the abyss of the galaxy. Its closest approach to Earth will be between 1.6 and 1.8 astronomical units, far enough to pose no threat, but near enough that our instruments can study it in detail. And yet, this is what unsettles the mind. 3 confirmed interstellar visitors in less than 10 years. In the year 2017 came Oumuamua, the very first such object ever recognized by human science. Astronomers of the time spoke of it as a once-in-a-lifetime encounter, a cosmic rarity unlikely to repeat for centuries. But just 2 years later, in 2019, the sky delivered 2Y, Borisov, another fragmentary exile from the interstellar deep. 2 interstellar objects in 2 years stretched the definition of improbable. And now, with the arrival of 3I Atlas, we find ourselves confronted with 3 in 8 years. Either our telescopic surveys have suddenly become miraculously efficient, or something else is happening, something that reshapes our assumptions about how empty the void between stars truly island. Early observations with the Hubble Space Telescope painted 3I Atlas in familiar colors. It resembled a comet, a fragile nucleus, perhaps 5 or 6 kilometers wide, though estimates suggest it might be as small as 320 meters, cloaked in the dusty shroud of sublimating ice. To mainstream astronomy, this was perfectly ordinary, a chunk of primordial matter cast adrift from some distant system billions of years ago, wandering until chance delivered it to our skies for a single fleeting passage. But appearances can deceive, and those who recall the mysteries of earlier visitors know the dangers of settling too quickly on easy classifications. Scientists now list 3I Atlas among cometary objects, its features fitting well enough with expectation. But in the margins of research papers and in quiet conference discussions, questions stir. Subtle deviations in brightness, small irregularities in trajectory. These anomalies may hold clues that simple labels cannot capture. We have walked this path before. Oumuamua, the herald of 2017, confounded astronomers with its elongated shape, its erratic tumbling, and most of all, with the faint but undeniable acceleration that carried it away from the Sun in defiance of gravitational law. Explanations proliferated. Some argued it must have been jets of evaporating ice, invisible plumes pushing it like sails. Others pointed to solar radiation pressure, photons striking its surface with unlikely efficiency. And still others entertained possibilities that skirted the line between science and speculation. These questions stretch beyond the neat diagrams of orbital mechanics. If the interstellar visitors are natural, then they are emissaries of geology and chemistry rather than of intent. They are fragments of alien worlds, debris flung from systems we will never visit, bearing within them the frozen fingerprints of stellar nurseries scattered across the Milky Way. In studying them, we glimpse a galactic recycling program at work, matter born in one star system, wandering across eons until it drifts through another. Each such object becomes a message in a bottle, whispering of environments unseen and planets forever hidden from our telescopes. Yet some scholars insist that we cannot ignore the other possibility. What if not all of these visitors are the product of blind physics? Harvard astrophysicist Avi Loeb has spent years urging that technological hypotheses deserve space in the scientific conversation, not because alien machines are the simplest explanation, but because they cannot be ruled out without the same rigor we apply to every other scenario. His Galileo project was conceived in the wake of Oumuamua's puzzles, a dedicated effort to seek hard data rather than dismissing the extraordinary out of hand. What if we are not alone? The question has echoed through human history, but here, in the faint trails of objects like 3I Atlas, It sharpens into something tangible. If civilizations older and wiser than ours exist elsewhere in the galaxy, how might they study younger worlds? Perhaps in the same way we study wildlife on Earth from a distance, careful not to disturb, with instruments that observe silently. In theoretical literature, such devices have names: lurker probes, Bracewell probes, machines that might wait in the shadows of planetary systems for millennia, keeping patient watch over the rise and fall of species, cataloging the birth and death of worlds. As 3i Atlas traces its arc across our skies, we are left with the haunting recognition that we may not simply be observing rocks and ice from afar. We may, without yet knowing, be observed in turn. The truth of these visitors, whether natural, technological, or something beyond both, remains hidden for now, carried with them as they vanish once more into the silence of the galaxy. It is a scenario that resonates with one of the most haunting attempts to answer the Fermi paradox, the dark forest hypothesis. Within this vision of the cosmos, the galaxy teems with civilizations, but each remains silent, not because they are inherently peaceful, but because they are cautious. To announce oneself by sending signals into the void is to risk becoming prey. In a dark forest, the safest course is to hide, to move quietly, to extinguish one's fire. For an intelligent species, broadcasting its existence could well be the final act it ever performs. These concepts dwell at the frontier between rigorous science and speculative thought. They stretch across the boundary of what can be imagined when physics, biology, and the vast architecture of space are brought into the same frame. And they shape the way we interpret visitors like 3i Atlas, whether this object proves to be a fragment of ancient ice or something far stranger. The sober truth is that we are probably looking at debris, the scattered remnants of some distant system, ice and stone born billions of years ago, flung into interstellar exile when our sun itself was young, now passing through our neighborhood by chance. The galaxy has always been recycling matter from one system to another, ever since the first stars died and scattered their ashes into the void, but probably is not the same as certainly. In the study of cosmic enigmas, that distinction matters more than most people realize. Over the next several months, as 3i Atlas makes its close approach to the sun, instruments across the world will be trained on it. Telescopes will trace its arc through space. Spectrometers will dissect the light bouncing off its surface and the gases streaming from its coma. Radio dishes will listen for whispers that might separate this wanderer from the class of ordinary comets. The expectation is that the data will confirm the obvious, that 3i Atlas is exactly what it appears to be, a natural traveler from deep space, carrying within its ice and dust the chemical stories of worlds born long ago. Yet the door to mystery remains open. What if, the more carefully we look, the less sense it makes? What if 3i Atlas, like Oumuamua before it, resists our neat categories and refuses to behave as it should? What if its signals, whether in motion, structure, or light, provoke more questions than answers? In the months to come, these questions will guide us deeper into the mechanics of interstellar wanderers, into the ongoing debates that animate the scientific community, and into the profound implications of life in a galaxy where such visitors have become almost commonplace. We will ask whether we are witnessing not isolated anomalies, but the first signs of a vast, unseen population of such objects moving steadily through interstellar space, only now revealed by the sensitivity of our instruments. And we will entertain the more speculative thought that some of these wanderers may not be natural at all, that they may hint at intelligence capable of spanning the gulf between the stars. Even now, 3i Atlas is hurtling sunward at a velocity that would incinerate any machine humans have ever built. In a few months, it will skim past our star, accelerate once more, and begin its long retreat into the darkness between worlds. Long before it reaches the outer edge of our solar system, every living human today will already have vanished into history. And yet, far away, another system will one day catch its light. Another civilization may note its passage as it drifts across their skies. A silent messenger from the neighborhood of our Sunday star. The story begins here, and we are its witnesses. The Atlas Telescope facility at Rio Hurtado, Chile, operates on a principle both stark and sobering. The universe is not a gentle place, and our best defense is vigilance without pause. Atlas, the asteroid terrestrial impact last alert system, watches the heavens methodically, sweeping the night sky for threats that might one day intersect Earth's path. Most nights, the system's discoveries are unremarkable, routine entries in the vast ledger of celestial mechanics. It catalogues main belt asteroids whose elliptical orbits never stray close enough to matter, space rocks locked into predictable trajectories, harmless reminders of cosmic debris drifting endlessly through the void. The night of early July in the year 2025 began in much the same fashion. Automated software surveyed familiar constellations, its algorithms tirelessly separating meaningful signals from the noise that plagues ground-based astronomy. Streaks from satellites, flashes from cosmic rays, detector glitches, and countless other artifacts masquerading as significance. Then came something that refused to be dismissed. A faint speck in the constellation Sagittarius, moving swiftly against the fixed stars, betrayed itself. The computers flagged it, and at first glance it seemed like another candidate for the catalogue of ordinary wanderers. But when astronomers fed its positional and velocity data into orbital models, the numbers refused to bend to expectation. The results were extraordinary. The object was not following an ellipse, the classic signature of gravitational bondage to the Sunday, nor was it on a parabolic curve that might return in millions of years. Instead, its motion described something far more unsettling, a hyperbolic trajectory. Atlas telescopes confirmed the data, and independent verification soon arrived from Caltech's Zwicky Transient Facility at Palomar Observatory. By stitching these observations together, astronomers were able to reconstruct the object's path into the outer solar system. Each data point carried the same conclusion, as sharp and undeniable as chisel marks in stone. This was no native of our sun's domain. Orbital mechanics is merciless in its clarity. Bound objects obey specific curves when velocity is plotted against distance. A comet ejected from the Oort cloud may take millions of years to swing through the inner system, but it will always slow as it climbs outward and accelerate as it falls back. The rules are absolute, but this object, soon to be named 3I Atlas, broke those rules. Its arc through space resembled a slingshot without return, the unmistakable imprint of an interstellar traveler. To imagine its situation, think of throwing a ball straight up from Earth. No matter how powerful the throw, gravity always wins, slowing it until it reverses course. Unless, of course, you could hurl it at 25,000 miles per hour, Earth's escape velocity. Then the ball would never return, instead carving a hyperbolic flight into the endless sky. That is precisely what 3I Atlas is doing, but on a scale of suns and planets. Its speed is too great for the sun to hold. It came from the stars, and it will leave for the stars once more. The Hubble Space Telescope soon turned its gaze toward this fleeting guest. Early images revealed the classic silhouette of a comet, a dense nucleus swaddled in a glowing coma of dust and gas, the product of ice vaporizing in solar heat. Estimates placed the nucleus at roughly 5.5 kilometers across, though it might be as small as 320 meters, an uncertainty born of distance and faintness. Compared to Oumuamua, with its baffling elongated form and inexplicable acceleration, 3I Atlas seemed almost reassuring. A comet from another star system, behaving exactly as the models had long predicted. Yet even here, comfort is relative. Interstellar comets are not supposed to be commonplace. Until 2017, they were theoretical, whispered about in equations but unseen. Oumuamua shattered that silence. 2 years later, Borisov followed. And now, within 8 years, we count 3 confirmed visitors from beyond. The transition from hypothetical rarity to apparent routine unsettles more than it reassures. Public reaction to 3I Atlas was muted compared to the media storm that greeted Oumuamua. Perhaps the novelty had faded. Perhaps the term comet inspired less awe than the enigmatic strangeness of an object that defied categorization. Yet this familiarity is dangerous. Even when they appear ordinary, interstellar comets are anything but. Each one is a messenger, a frozen time capsule from a planetary nursery we will never witness directly. The chemical signatures locked in their ice and dust bear testimony to alien conditions, echoes of worlds born under other suns. 3I Atlas approached from the direction of Sagittarius, though the galaxy's rotation long ago blurred any hope of tracing its precise birthplace. It may have been adrift for millions, perhaps billions, of years, wandering vast corridors of interstellar space. To reach us, it traveled at least dozens of light years, perhaps hundreds, carrying within it the preserved memory of its origins. For perspective, light itself, the fastest thing known, takes years to decades to make such a journey. This tiny shard of rock and ice made the same crossing without fanfare, until fate steered it across our line of sight. Its discovery raises uncomfortable questions about cosmic demographics. If these objects were as rare as once thought, why have we now seen 3 in less than a decade? The answer may lie not in the objects, but in our evolving ability to detect them. Earlier surveys lacked the sensitivity, coverage, and computational power to capture faint, fast-moving travelers. But the coming of the Vera C. Rubin Observatory promises to change that forever. Its legacy survey of space and time will sweep the entire visible sky every 3 nights with unprecedented resolution. Predictions suggest we might find 1 or 2 interstellar objects each year, perhaps more, perhaps dozens under optimistic conditions. The truth is, we simply do not know how many of these wanderers exist, drifting silently between the stars. And so, 3I Atlas falls sunward at 137,000 miles per hour, trailing its luminous veil of dust and gas. It appears ordinary, and yet, by definition, it is extraordinary. Observatories across the planet will dissect its light, measure its gases, and listen in radio silence for signs that distinguish it from natural debris. Most likely, the data will confirm that it is nothing more than a comet, a refugee from another star system. But most likely is not certainty. In the realm of cosmic mysteries, certainty is rare, and surprises wait in every line of data. The night sky still conceals more secrets than we dare imagine, and 3I Atlas reminds us how little we truly know of the universe we inhabit. From Oumuamua to 3I Atlas, the story of interstellar visitors is written in a timeline where timing itself matters more than most people realize. It begins on the 19th of October in the year 2017, when the Pan-STARRS 1 telescope in Hawaii detected something that would alter astronomy forever. 1I Oumuamua, the first confirmed interstellar object ever observed passing through our solar system. At first, Oumuamua appeared deceptively inert. It showed no visible coma, no hazy shroud of vaporizing ice, suggesting it was either an exhausted comet or something else entirely. Shape models hinted at an astonishing geometry, an object perhaps 10 times longer than it was wide, tumbling end over end through the void like a cosmic cigar. But Oumuamua saved its greatest mystery for its departure. As it receded from the sun, it displayed a faint but measurable acceleration, a push that gravity alone could not explain. It was only a few centimeters per second squared, subtle and barely detectable, yet it ignited years of fierce debate about what forces could be driving such behavior in an apparently inert rock. 2 years later, on the 30th of December in the year 2019, a new discovery arrived, not from a giant survey telescope, but from the dedication of an individual. Amateur astronomer Gennady Borisov, working in Crimea with a 65-centimeter telescope he had built himself, found the second interstellar traveler, 2I Borisov. Unlike Oumuamua, Borisov conformed neatly to astronomers' expectations. It looked like an active comet, displaying a classic coma and tail, its behavior predictable as it drew near the sun. Yet even this apparently conventional visitor carried surprises. Spectroscopic analysis revealed a strikingly high abundance of carbon monoxide compared to comets within our own solar system. That unusual chemistry suggested it had formed in a colder environment than any found nearby, giving scientists their first direct evidence of planetary formation conditions different from those that shaped our cosmic neighborhood. Then, on the 1st of July in the year 2025, the Atlas survey in Chile reported the discovery of a third traveler, 3I Atlas. Like Borisov, it displayed the telltale signs of a comet, an active nucleus shrouded in dust and vapor, its size estimated somewhere between 320 meters and 5 or 6 kilometers. Its trajectory, however, was unmistakably hyperbolic, inbound from the general direction of Sagittarius. 3 interstellar visitors in less than 8 years. Before Oumuamua, these objects existed only in theory. Astronomers had long assumed that planetary systems, in the violence of their formation, would eject countless fragments into interstellar space, but these remained hidden in equations and speculative models. The leap from theoretical possibility to confirmed reality changed the field overnight. The conventional explanation for this sudden abundance is not that the galaxy suddenly grew more generous with its wanderers, but that our instruments finally became capable of catching them. For most of human history, our searches were too shallow, our telescopes too narrow, our cadence too infrequent to notice faint, fast-moving interstellar debris. Before Rubin-era surveys, astronomy was like trying to watch a meteor shower through a keyhole limited in field of view, sensitivity, and timing. Countless interstellar visitors may have slipped past unnoticed, their brief appearances unmarked by the instruments of the time. That explanation is almost certainly correct. Almost. And almost leaves just enough space for doubt, for alternative interpretations that are far more unsettling. Because if it is not simply selection bias, then something about the galaxy itself may be changing. The Vera C. Rubin Observatory, now preparing to embark on its legacy survey of space and time, will radically shift what we know about transient phenomena. Beginning in the year 2025, Rubin will map the entire visible sky every 3 nights, wielding an 8.4-meter mirror and a 3.2 gigapixel camera sensitive enough to see objects hundreds of times fainter than those detected before. Conservative models predict that Rubin will reveal 1 or 2 interstellar visitors every year. More optimistic analyses, accounting for higher ejection rates and broader galactic populations, suggest dozens annually. The most ambitious projections push the number to 70 per year. Such staggering uncertainty reflects the fragility of our current knowledge. We are extrapolating the population of an entire galaxy from a sample size of 3, but consider again the timing. 3 objects in 8 years, discovered with surveys that are still limited compared to what Rubin will achieve. If the predictions hold, and Rubin detects only 1 or 2 per year, then the older models are validated, and the three we have already found represent chance alignments and better observational power. But if Rubin starts detecting dozens annually, the picture shifts. The interstellar medium may be far denser with objects than we ever dared imagine. And if the count climbs into the hundreds, the implication would be staggering. That the galaxy is not a sparse scattering of isolated star systems, but a dynamic ecosystem, a vast archipelago of stars bound together by the steady flow of matter moving between them. The implications reach beyond simple counting. Each visitor carries clues to its origins. Borisov's chemistry hinted at environments colder than those in our solar system. Future discoveries will bring more data points, mapping the chemical and structural diversity of planetary formation across the Milky Way. But lurking in the background is the speculative possibility that refuses to fade. What if the increase in detections is not just an observational artifact? What if we are seeing the first wave of something larger, an authentic rise in interstellar traffic? Natural mechanisms could account for temporary increases, gravitational focusing, galactic dynamics, unseen stellar encounters, but the timing still provokes questions that science alone may not yet be able to answer. 3 visitors in less than a decade, each one different, each one stranger than expected, and together they hint that our solar system is not the quiet cul-de-sac we once imagined. Instead, it may be a crossroads, brushed again and again by wanderers from the deep night, each carrying with it a fragment of another world, and the possibility that the galaxy itself is alive with motion, with memory, and perhaps with intent. The Sun's long orbit around the Milky Way does not simply carry our solar system through empty space. Its motion could sweep us into regions where the density of interstellar debris is higher, places where fragments from other stellar nurseries drift more thickly through the void. Stellar encounters, although infrequent on human timescales, may also play a role. A passing star brushing close to our outer Oort cloud could jostle comets free, perturbing them into new trajectories or even injecting material into interstellar space. Such processes occur over millions of years, but on cosmic scales, they could very well be relevant to the pattern of recent detections. Yet beyond these natural explanations lies a more speculative possibility, one that brushes against the central questions of astrobiology. What if some interstellar objects are not natural fragments at all? What if a fraction of them are technological artifacts, the silent products of civilizations beyond our own? The idea sounds like the domain of science fiction, but serious scientists have argued that it deserves consideration. Harvard astrophysicist Avi Loeb has been among the most vocal, pressing the case that technological hypotheses should be treated as testable, not taboo. His Galileo project embodies this approach, aiming to apply rigorous observational astronomy to questions long confined to speculation. If even a handful of interstellar visitors are technological in origin, their growing frequency might not be a quirk of survey sensitivity, but a reflection of galactic reality. Civilizations that advance into space often grow more active over time. They launch probes, explore star systems, send instruments to survey planets, moons, and perhaps life. From this perspective, the increasing detection rate of interstellar objects could be the signature of galactic exploration, not merely cosmic chance. This reframes the famous Drake equation. Instead of asking how many civilizations are attempting to communicate with us through deliberate signals, we might instead ask how many are actively exploring. Communication and exploration serve different purposes and involve different risks. A civilization that chooses to explore may remain silent about its own presence, gathering data quietly while preserving its anonymity. Such a strategy fits with several proposed solutions to the Fermi paradox. The galaxy may feel silent not because intelligence is absent, but because prudence dictates stealth. These ideas lie at the edge of speculation, but they are grounded in the discipline of scientific reasoning. Speculation, when tethered to observation, functions as a compass. It points toward the questions most worth asking and the measurements most worth making. Over the next decade, as the Rubin Observatory begins its deep survey of the sky, we will learn whether the pattern we have observed is fleeting or enduring. The answer will determine whether interstellar space is as barren as tradition once taught us, or whether it is alive with matter and perhaps intelligence, moving far more freely than we dared to imagine. Whatever we find, our understanding of the cosmos and of our place within it will be reshaped forever. Physics rests on rules so elegant and universal that they feel almost like poetry. Objects in motion continue in motion unless acted upon by an external force. Gravity diminishes with the square of distance. Energy cannot be created or destroyed, only shifted from one form into another. These principles govern everything we know, from the fall of an apple to the orbit of planets, and even to the journeys of the strange interstellar visitors that pass through our skies. So when an object behaves in ways that refuse to fit those rules, astronomers notice and they do not let go. Oumuamua's anomalous acceleration remains one of the most scrutinized enigmas in modern astronomy. As the elongated body retreated from the Sun in late 2017, careful astrometric measurements revealed that it was moving slightly faster than gravity alone could account for. The excess was minuscule, mere centimeters per second squared, but in the realm of celestial mechanics, even such tiny deviations cry out for explanation. Imagine a hockey puck sliding across ice toward a campfire. You would expect its speed to hold steady, perhaps diminish slightly as friction worked against it. You would not expect the puck to accelerate as it warmed. And yet, that is precisely the riddle Oumuamua presented. It gained speed in a place where only deceleration seemed possible. The obvious explanation for such non-gravitational forces is outgassing, the process by which comets release jets of vaporized ice, acting like microscopic thrusters. But Oumuamua revealed no visible coma, no tail, no shimmering plume of water vapor that would explain the push. It was as if the usual playbook had been set aside. For years, scientists debated. Some proposed exotic ideas. Pressure from sunlight nudging an object with an unusually light and broad surface, or interactions with the sun's magnetic field. Others ventured into speculation, suggesting Oumuamua might be artificial, a technological artifact designed to alter its own trajectory. Then, in 2023, a team led by Jennifer Bergner and Daryl Seligman proposed a solution both simple and elegant. Over millions of years adrift in interstellar space, cosmic rays may have bombarded Oumuamua's icy body, breaking water molecules apart and trapping hydrogen gas within its structure. When warmed by the sun, this hidden hydrogen would sublimate and escape, providing thrust without producing the visible water vapor jets normally associated with comets. Hydrogen is nearly invisible to most telescopes, which explained why astronomers saw acceleration without signs of outgassing. The model fit the energy budget, obeyed known physics, and resolved the mystery without resorting to speculation. Most of the community accepted it as the most plausible explanation, though skeptics noted that it required Oumuamua to have both a porous structure to trap gas and a strong enough framework to survive eons of interstellar bombardment. Possible, but not inevitable. By contrast, 2Y Borisov arrived like a reassuring confirmation of the ordinary. Discovered in 2019 by amateur astronomer Gennady Borisov, this interstellar comet displayed all the familiar hallmarks of its solar system cousins: a bright coma, a streaming tail, predictable outgassing as it neared the sunday. Its orbit fit the rules, its behavior conformed to expectation, and yet it too carried its own lesson. Spectroscopic studies revealed unusually high levels of carbon monoxide, far greater than those typically observed in comets born under our Sunday. The chemistry suggested it formed in a far colder environment, perhaps near the edges of its parent star's system. Borisov's normalcy was, in its own way, just as profound as Oumuamua's strangeness. It demonstrated that interstellar visitors could fall neatly within established laws, proof that the universe itself had not shifted, but that our sampling of it was expanding. Now, in the summer of 2025, comes 3I Atlas, detected by the Atlas survey and quickly confirmed by follow-up observations. It speeds toward the Sun at 137,000 miles per hour. To telescopes, it looks comfortingly like a comet, a solid nucleus wrapped in a hazy coma, shedding dust and vapor in the Sun's heat. The Hubble Space Telescope captured its glowing form, displaying the very features that Oumuamua conspicuously lacked. Spectroscopic analysis will in time reveal its chemical makeup, offering yet another piece of the puzzle of how planetary systems across the galaxy forge their icy debris. But appearances can deceive. The mathematics of its orbit declare its foreignness with precision. Its hyperbolic excess velocity, the speed it will retain after the Sun's pull has done its work, measures about 58 kilometers per second. That is fast enough to cross the Earth, moon distance in roughly 2 hours. For an interstellar object, such speeds are not unusual, but they are definitive. 3I Atlas did not arise from the Sun's family. It came from elsewhere, likely traveling for millions of years through the galactic dark before arriving at our doorstep. Its trajectory traces back toward the general region of Sagittarius, but galactic rotation scrambles origins beyond recognition. After so many eons, no astronomer can point to its birthplace with certainty. It has wandered free, sculpted only by the gravitational nudges of stars and planets encountered along the way. Models of planetary system formation predict that such wanderers should exist. In the chaotic youth of star systems, giant planets shift their orbits dramatically, scattering smaller, icy bodies into wild trajectories. Some are flung inward to collide with nascent worlds, others are tossed outward, and a fraction achieve escape velocity altogether, cast adrift into the galaxy. Over billions of years, this process has filled interstellar space with a population of vagabonds, cold relics, chemical archives of alien nurseries, silent witnesses of the galaxy's restless youth. 3I Atlas joins Oumuamua and Borisov as part of a growing catalogue of such objects, each one expanding the boundaries of what we know. Together they remind us that the rules of physics remain intact, but the universe is larger, older, and more diverse than the narrow confines of our solar system once suggested. They are travelers from afar, messengers of other suns, and their fleeting passages invite us to measure, to question, and to wonder what else might be out there, waiting its turn to pass silently through our skies. Predictions about how many interstellar visitors we should expect to see have always carried wide margins of uncertainty. Different models, built on different assumptions about how efficiently planetary systems eject debris and how long those fragments survive, lead to vastly different outcomes. Some suggest we should encounter one interstellar object every year. Others argue such events should be once-in-a-century rarities. The fact that we have detected 3 in only 8 years seems to favor the more optimistic models, but the sample size remains far too small to declare victory. The Vera C. Rubin Observatory promises to change this. By delivering unprecedented sky coverage and sensitivity, it will build the large-scale statistics needed to test population models against observational reality. Yet the challenge is not only in counting visitors, but in recognizing when one behaves in ways that defy expectation. If an object refuses to outgas like a normal comet, or if its thrust patterns diverge from what solar heating of water ice should produce, those are anomalies worth investigating. Oumuamua gave us precisely such a case, with its unexplained acceleration. While the hydrogen outgassing model now offers a natural mechanism, the episode demonstrates how easily mysteries can slip through gaps in our knowledge. Future interstellar travelers may present their own puzzles, anomalies not so easily reconciled with current physics. The key lies in maintaining scientific discipline, favoring natural explanations when consistent with data, but never discarding anomalies simply because they complicate existing theories. This is where science advances most at the boundary between expectation and surprise. So far, 3-1 Atlas has played by the rules. Its trajectory obeys gravity's script, its outgassing fits the patterns of ordinary comets, and its approach geometry aligns with models of debris ejected from young star systems. By all appearances, it is an ordinary interstellar comet. Yet appearances must always be provisional. As it nears its closest approach to the Sun on the 30th of October, 2025, increasingly sensitive instruments will probe its chemistry, track brightness variations that may reveal spin or jet activity, and listen across the radio spectrum for signals, natural or otherwise. Most likely, the evidence will confirm what we expect, that 3I Atlas is a fragment of ice and rock from another system, governed by the same physics that holds across the universe. But, most likely, is not the same as certain, and, in the realm of cosmic mysteries, that small distinction carries enormous weight. Abraham Avi Loeb occupies a singular space in modern astrophysics, at once an insider and an outsider. As the former chair of Harvard's astronomy department, a prolific scholar with hundreds of peer-reviewed papers, and a former member of the President's Council of Advisors on Science and Technology, Loeb's credentials are beyond reproach. His scientific reputation is firm, his institutional authority secure. And yet, in recent years, he has recast himself as astronomy's most visible provocateur, a figure whose willingness to entertain unorthodox possibilities has earned him both admiration and criticism in equal measure. Loeb's central argument is straightforward, even deceptively so. If science never entertains technological explanations for puzzling astronomical phenomena, then we may overlook the very evidence that could confirm the existence of extraterrestrial intelligence. To him, the scientific method is not about protecting our comfort zones, but about testing every plausible hypothesis. For some, this openness is refreshing, a necessary antidote to intellectual conservatism. For others, it is reckless, a flirtation with speculation that risks diluting the rigor of the field. The flashpoint was Oumuamua, when the object confounded astronomers with its mysterious non-gravitational acceleration in 2017. Loeb and his colleague Shmuel Bialy proposed one explanation that electrified the field. Perhaps radiation pressure was acting on an unusually thin, lightweight structure, something akin to a solar sail. In plainer terms, maybe Oumuamua was not a natural rock at all, but a piece of alien technology, or debris from such a device. The paper was careful, presenting this idea as one possibility among many rather than a definitive conclusion. Still, the implications were profound. If true, it would mark the first detection of extraterrestrial technology in human history. The astronomical community's response was swift and largely hostile. Many argued that natural explanations, however contrived, should be preferred over technological speculation. Occam's razor, the principle that simpler explanations are more likely to be correct, was invoked repeatedly. But Loeb refused to retreat. To him, the reflexive dismissal of technological hypotheses was not rigor but bias. Extraordinary claims require extraordinary evidence, he agreed, but insisted that extraordinary investigation was the only way to obtain that evidence. If no one bothered to look seriously, how could anyone ever know whether the extraordinary had been hiding in plain sight? In 2023, the hydrogen outgassing model proposed by Jennifer Bergner and Daryl Seligman offered what most astronomers considered a satisfying natural resolution to Oumuamua's behavior. Cosmic ray bombardment could have produced trapped hydrogen within its ice, which sublimated near the sun and provided invisible thrust. To most, the explanation was elegant and sufficient, but Loeb remained unconvinced. He noted that the model relied on assumptions about Oumuamua's internal structure and history that could not be independently tested. For him, the debate underscored a deeper issue: astronomy's lack of systematic searches for technological signatures. Astronomers routinely seek out exotic stars, unusual galaxies, or unexpected gravitational wave sources, yet few actively scan for artifacts that might reveal the handiwork of extraterrestrial engineering. This conviction inspired the creation of the Galileo project in 2021. Named after the revolutionary who first pointed a telescope toward the heavens, the initiative is designed to bring rigorous observational science to questions long relegated to the margins of speculation. Its mission is methodical: develop new instruments capable of detecting anomalous objects, establish protocols to distinguish natural from technological signatures, and assemble a database of observations subject to the same scrutiny applied elsewhere in science. The recent discovery of 3.1 Atlas has given Loeb new momentum. He argues that the era of passive observation should give way to proactive exploration. Specifically, he has urged space agencies to prepare interception missions capable of studying interstellar visitors up close. Concepts like Project Lyra, using gravity assists and advanced propulsion to chase down fast-moving targets, demonstrate that such missions are difficult but not impossible. Loeb insists the payoff would be immense. Only a close-range investigation could truly determine the composition, structure, and origins of such objects. Remote telescopes, however powerful, can only provide fragments of the full story. Yet critics remain steadfast. They point out that both Borisov and 3.1 Atlas have behaved exactly as theory predicted, displaying classic cometary signatures with no unexplained accelerations. Natural explanations have consistently sufficed, they argue, and introducing extraterrestrial technology without compelling evidence risks turning astronomy into a playground for speculation. Large-scale missions, they note, require decades of planning and vast sums of money, resources that could be misallocated if driven by extraordinary claims lacking extraordinary proof. In the end, Loeb embodies a tension at the heart of science itself: the balance between conservatism and boldness, between guarding established principles and probing the unknown. His voice forces astronomy to confront its biases, to admit that the question, "what if?" still matters. Whether his provocations prove prescient or misguided, they ensure that the search for interstellar truth will not be dulled by complacency. The criticism has weight. Science does not advance by seizing upon exotic explanations simply because they capture the imagination. It moves forward through careful hypothesis testing, patient accumulation of data, and rigorous analysis. Astronomy's own history provides a catalogue of cautionary tales. Pulsars were once dubbed LGM, little green men, because their regular signals seemed almost artificial. Gamma-ray bursts and fast radio bursts were at first shrouded in mystery, inspiring speculation about alien beacons. In every case, sustained observation and theoretical progress revealed natural mechanisms: neutron stars spinning with clockwork precision, cataclysmic stellar explosions, exotic astrophysical processes. The lesson is clear: Mysteries often dissolve under the steady light of science. But Loeb's defenders argue that this history, while instructive, misses the crux of his position. The question is not whether natural explanations are more likely than technological ones. They almost certainly are. The real concern is whether the scientific community systematically ignores even the possibility of technological explanations because such ideas unsettle its intellectual comfort. If so, then astronomy risks blinding itself to data that could be the most significant in human history. This debate reflects a deeper tension running through modern astrophysics, the balance between conservatism and exploration. Conservative methods are designed to minimize false positives, the error of mistaking natural phenomena for artificial ones. This caution protects science from wild speculation, but it comes at a cost, for it maximizes the risk of false negatives, failing to recognize genuine technological signatures because they fall outside established search frameworks. Loeb insists the stakes are too high to tolerate such omissions. If extraterrestrial civilizations exist, and if they are actively probing the galaxy, then overlooking evidence of their presence would constitute one of humanity's greatest scientific oversights. His principle is stark. Better to investigate 100 natural anomalies unnecessarily than to dismiss one artifact of intelligence. This principle carries practical consequences for how we study objects like 3I Atlas. Most observational programs are content to characterize size, composition, rotation rates, and outgassing patterns, measurements that build our understanding of interstellar populations regardless of origin. Loeb calls for a parallel set of investigations aimed explicitly at testing technological hypotheses. Radio telescopes should listen for narrowband emissions that could betray communications or power systems. Infrared instruments should scan for excess heat that might indicate internal energy sources. Precision astrometry should test for trajectory changes inconsistent with solar heating or gravity, clues that could suggest propulsion or attitude control. None of these would, by themselves, prove artificiality. Natural phenomena could explain nearly any observation, but without such data, the question is never meaningfully asked. The controversy surrounding Loeb's stance thus opens into a larger philosophical question. What role should speculation play in science? Too much deviation from orthodoxy can erode rigor, turning astronomy into science fiction. Too little deviation risks stagnation, ensuring that discoveries which fall outside current categories are missed or ignored. Science thrives in the space between, in the tension between bold hypothesis and skeptical testing. Loeb's provocations force astronomy to examine whether its balance has tilted too far toward caution. What is certain is that the discovery of interstellar objects has broadened the field's horizons. Before Oumuamua, they were theoretical curiosities. Now, with 3 detections in 8 years, they are established features of the cosmic landscape. Whether they prove to be mere relics of planetary formation or something altogether more extraordinary, they demand new strategies of investigation. As 3I Atlas approaches its closest pass by the Sun on the 30th of October in the year 2025, telescopes worldwide are preparing for the moment. Spectroscopy will reveal its chemistry, photometry, its spin and activity, radio astronomy, its silence, or, just possibly, its signal. The smart money says it will behave like a comet, a frozen messenger carrying chemical signatures from another stellar nursery. But likely is not certain. In a universe that has already surprised us 3 times in less than a decade, the possibility of further surprises must be taken seriously. The debate between conventional astronomy and Loeb's more speculative approach will not be settled by this one object. It will continue, shaping how we frame our questions and design our searches. But the stakes could hardly be greater. In a galaxy filled with hundreds of billions of stars and, perhaps, millions of civilizations, the question of whether we are alone has shifted from philosophy into the realm of observation. The answer may already be in the data, waiting for those willing to look with both rigor and courage. Imagine yourself deep in a forest, a wildlife biologist tasked with studying elusive animals. You would not announce your presence with floodlights or loudspeakers, because doing so would destroy the very behaviors you hope to observe. Instead, you would set up motion-triggered cameras, camouflage your blinds, and keep your distance, careful to remain invisible. The goal is to see life unfold unaltered, to witness patterns as they are, not as they become under scrutiny. Now, magnify that principle to the scale of galaxies. If advanced civilizations exist elsewhere in the cosmos, how might they study primitive planets like Earth? Almost certainly in the same way, through careful, concealed observation, instruments designed not to intrude but to record, patient enough to operate over spans of millennia. In the scientific literature, such concepts are formalized as Lurker probes or Bracewell probes, after physicist Ronald Bracewell, who articulated the idea in 1960. Instead of shouting across interstellar space with powerful radio beacons costly in energy and fraught with risks, civilizations might instead send robotic emissaries into promising star systems. These silent sentinels could study planets for thousands, even millions of years, gathering data on geology, climate, biology, and the rise of intelligence before quietly transmitting the findings back home. The approach mirrors science's highest aspiration: observation without interference. Engineering such devices would be no trivial feat. To endure geological timescales, they would require power systems stable over millions of years, communication technologies capable of spanning light years, and camouflage strategies sophisticated enough to avoid detection by the very civilizations they monitor. One elegant solution would be to disguise themselves as natural objects. A probe, masquerading as an asteroid, could tumble randomly, mimic thermal patterns consistent with solar heating, and shed no detectable emissions, except in the rare moments when communication or maneuvering was necessary. Biomimicry, a principle already familiar in human engineering, would ensure that such a device blended seamlessly into its environment. Power sources would present a separate challenge. Instead of reactors betraying detectable signatures, probes might rely on subtler systems, long-lived radioisotope generators, energy harvested from the solar wind, or, in the more speculative realm, quantum vacuum fluctuations. For data storage, the challenge is less daunting. Even modern humanity can encode exabytes of information into crystalline matrices durable for millions of years. One can only imagine what an advanced civilization might achieve. The real difficulty lies in communication. How does one transmit intelligence across dozens or hundreds of light years without exposing the probe to discovery? One possibility is tightly focused laser or microwave beams, detectable only by receivers in prearranged positions. Another is to encode data into orbital patterns, constellations of probes whose apparent randomness hides a structured signal comprehensible only to its creators. A more ambitious vision is a galaxy-wide network, where probes act as relays, passing information along chains of silent sentinels until it reaches its destination. Such a system could operate for eons without ever revealing itself to the planets it surveys. We have no evidence that Lurker probes exist. The idea remains speculative, a thought experiment that stretches imagination while staying tethered to plausible engineering principles. Yet it offers a compelling framework for rethinking objects like Oumuamua, Borisov, and 3I Atlas. If some interstellar objects were artificial, how could we distinguish them from natural debris? Natural wanderers should behave predictably. Their compositions match planetary formation chemistry. Their orbits follow gravity's dictates. Their activity reflects solar heating and outgassing. Artificial probes, by contrast, might betray themselves through anomalies, chemical compositions that defy expectation, accelerations not explained by physics, radiation signatures inconsistent with nature. But the very sophistication of any civilization capable of building such probes ensures that anomalies would be subtle. The goal of these devices would be concealment, not spectacle. An artificial probe would be designed to pass every test of naturalness. Its camouflage would be its strongest defense, ensuring that casual or even careful surveys would overlook its true nature. That creates the paradox of the search. How do you detect something that is specifically engineered to evade detection? The only answer lies in patience and persistence. Systematic, long-term monitoring of objects assumed to be natural could reveal faint irregularities, signals repeating on unexpected cycles, coordinated behavior across multiple bodies, subtle responses to triggers like radio emissions or spacecraft flybys. Only through vast datasets, collected and analyzed over decades, might patterns emerge that suggest design rather than chance. Yet current astronomical infrastructure is not optimized for this pursuit. Surveys like ATLAS, Pan-STARRS, or the forthcoming Rubin Observatory are built to discover and catalog natural objects, asteroids, comets, supernovae, variable stars. They are not designed to sift through terabytes of data for subtle anomalies that could betray an artificial origin. This does not mean the search is futile, only that a shift in perspective is required. Just as wildlife biologists learn to look for hidden traces of animals, not their direct appearances, astronomers may one day learn to design searches for signatures of intelligence concealed in plain sight. For now, the idea of lurker probes remains a theoretical construct, but it sharpens our imagination. It reminds us that the absence of evidence is not evidence of absence, and that the galaxy may hold secrets invisible to eyes trained only on the natural. In the faint arcs of objects like 3I Atlas, we glimpse the possibility that someone, somewhere, may already be watching quietly, patiently, and with a purpose we have yet to understand. That picture could shift as data processing techniques grow more sophisticated and as the search for extraterrestrial intelligence evolves from speculation into systematic investigation. The hypothesis of lurker probes provides a provocative reframing of the Fermi paradox, that enduring puzzle of why a galaxy so ripe for life seems so silent. If advanced civilizations value surveillance over open communication, then the apparent silence may be an illusion. The galaxy could be crowded with intelligence, yet appear quiet to observers like us. In such a scenario, the absence of detected radio signals would no longer be surprising. Civilizations practicing stealth would never broadcast indiscriminately, unwilling to risk exposing their presence to unknown neighbors. Their communications would be tightly focused, encoded, or transmitted through methods invisible to our instruments. To us, the sky would remain silent even as it hummed with activity beyond our reach. The implications run deeper than detection alone. If lurker probes exist and have been stationed in our solar system for thousands or even millions of years, then they would have witnessed humanity's entire technological ascent. They would hold records of our atmosphere warming under industrial activity, of mushroom clouds blossoming over battlefields, of spacecraft escaping Earth's gravity for the first time. They would see us as a species on the threshold, wielding tools powerful enough to shape our destiny, yet still struggling to master them responsibly. In such archives, humanity might appear not as a finished civilization, but as a case study in adolescence, its future uncertain, its choices decisive. This line of thought remains highly speculative. We have no direct evidence for lurker probes, nor any clear way of falsifying the hypothesis with current technology. Yet the value of the idea lies in how it broadens the conversation. It forces us to imagine forms of cosmic intelligence that go beyond traditional SETI assumptions of deliberate broadcasts. As our capacity to monitor interstellar objects improves, we may one day develop techniques capable of distinguishing natural debris from subtle technological artifacts. Until that day, objects like 3I Atlas remain what they appear to be: icy fragments from distant star systems, carrying within them the chemistry of alien worlds. And yet, the question lingers. What if some of those fragments are not merely chemical messengers, but silent cameras watching us still, whispers in a dark forest? Imagine yourself alone in the wilderness at night, sitting beside a small campfire. The flames offer only a fragile circle of light, while beyond, the shadows are alive with movement. You hear creatures in the underbrush, their identities concealed. Do you call out, announcing yourself to whatever lurks in the dark? Do you raise a torch and flood the woods with light, revealing not only them but also yourself? Or do you shrink your fire, keep silent, and listen carefully, trying to discern whether those sounds signal curiosity, indifference, or danger? This is the metaphor that lies at the heart of the dark forest hypothesis, a vision popularized by Chinese science fiction author Liu Cixin, but rooted in earlier scientific speculation about extraterrestrial intelligence. The hypothesis begins with sobering logic. Faster than light travel, if not outright impossible, is at least extraordinarily difficult according to our current understanding of physics. That means civilizations scattered across the galaxy cannot rely on quick communication or swift diplomacy. In such an environment, any contact between civilizations becomes a high-stakes game of incomplete information. You cannot know the intentions of those you encounter. What you do know is that advanced civilizations, by definition, command advanced technologies, and thus advanced weapons. Distance may provide some buffer, but it does not guarantee safety. A civilization with millions of years to plan could unleash relativistic projectiles, self-replicating machines, or other weapons well within the limits of known physics to sterilize distant star systems. The threat need not be imminent to be existential. Under these conditions, broadcasting your presence becomes risky in the extreme. Yes, you might attract peaceful neighbors eager for trade, knowledge, and exchange, but you might also summon predators who view other civilizations as rivals to be destroyed or resources to be harvested. The safest strategy, dark forest logic concludes, is silence. Thus emerges a galaxy potentially crowded with intelligence yet shrouded in stillness. No broadcasts, no dazzling megastructures blazing across interstellar distances, nothing that might betray existence to unknown neighbors whose motives cannot be trusted. Every civilization, then, becomes both hunter and hunted, lurking in a forest where every spark of light could invite destruction. It is a bleak vision, one where paranoia prevails and cooperation is smothered before it can begin. Yet its pessimism does not automatically render it false. After all, evolution itself is driven by competition, predation, resource struggles, and survival pressures shape species long before intelligence emerges. Why should intelligence erase those instincts rather than refine them? If survival remains the ultimate imperative, suspicion may be the most rational strategy. Still, critics highlight several fragile assumptions underlying this view. It presumes that most civilizations, across countless evolutionary pathways and cultural contexts, would converge on the same cautious behaviors. It assumes that advanced intelligence will inevitably interpret other civilizations as threats rather than potential allies. And it presupposes that the benefits of concealment outweigh the potential rewards of contact rewards that could include trade, cultural enrichment, and shared scientific progress. More fundamentally, the hypothesis projects scarcity thinking onto civilizations that may no longer be bound by scarcity. A species capable of harnessing the energy of entire stars, a civilization operating on Kardashev scales, may not view resources as limited in the same way we do. For them, information itself, new discoveries, unique cultures, artistic creativity, philosophical perspectives could represent the most precious commodity. From such a standpoint, contact with others might be sought out not for conquest but for enrichment. And yet even critics admit that dark forest reasoning could hold true in certain contexts. Young civilizations emerging directly from evolutionary struggle may carry aggressive instincts forward, prioritizing survival above cooperation. Species formed in resource-starved environments may develop expansionist imperatives to secure long-term survival. Others, scarred by encounters with hostile neighbors, may adopt silence as a permanent shield. The unsettling implication is that the existence of even a handful of predatory civilizations could be enough to poison the well. If aggressive species destroy or assimilate peaceful ones, the galactic landscape eventually becomes dominated by those who follow expansionist, survivalist strategies, even if they began as a minority. In this light, the dark forest hypothesis becomes more than a metaphor. It offers one possible resolution to the Fermi paradox, the great silence that perplexes us. Despite the high probability of extraterrestrial life, we see no evidence of civilizations. Perhaps it is not because they are absent, but because they, like us, sit by their campfires in silence, listening to the whispers in the darkness, waiting, wondering, and fearing what might answer if they call out. If most civilizations in the galaxy adhere to stealth protocols, they would not construct detectable megastructures, flood space with high-powered radio broadcasts, or engage in activities visible across interstellar distances. They would remain quiet, patient, and concealed. This logic, however, forces us to confront uncomfortable questions about our own behavior. Humanity has been leaking radio signals into space for more than a century. We have sent deliberate messages to nearby stars. We are building telescopes capable of detecting Earth-like planets, and we are developing techniques that could one day reveal not only the atmospheres of those worlds, but perhaps signs of life itself. From the perspective of the dark forest hypothesis, such activities could be interpreted as reckless. By calling attention to ourselves, we may be signaling to the galaxy that we are a potential threat to be neutralized or a resource to be exploited. The concern is not merely theoretical. Some prominent scientists, including Stephen Hawking, have explicitly warned against active SETI, the deliberate broadcasting of signals meant to announce our existence. Their caution mirrors dark forest reasoning. We do not know what is out there, and the first encounter may not unfold the way our more optimistic imaginations suggest. Yet others dismiss such worries as exaggerated. They argue that any civilization advanced enough to threaten us across interstellar distances would already have detected our presence from decades of radio leakage and atmospheric signatures. If such civilizations wanted us gone, they would not have waited. Moreover, the physics of interstellar warfare may not favor offense as cleanly as dark forest scenarios imply. Relativistic projectiles, while devastating, can also be tracked and potentially intercepted. Self-replicating machines could be matched by defensive counterparts. Even for civilizations with technology far beyond ours, launching attacks across dozens or hundreds of light years would be slow, costly, and uncertain. Defense, in other words, might be more feasible than fear suggests. The debate points to deeper uncertainties about intelligence itself. Do species inevitably carry forward the competitive instincts of evolution, treating others as threats to be eliminated? Or does intelligence allow them to transcend those instincts, cultivating cooperation and coexistence? Are advanced civilizations driven primarily by hunger for resources, or do they pursue goals so far beyond human comprehension that our categories of predator and ally no longer apply? These questions sharpen when we consider interstellar visitors like Oumuamua, Borisov, and 3I Atlas. If even a fraction of such objects were artificial, then what strategies might their makers have followed? Dark forest reasoning suggests that reconnaissance probes would aim for perfect camouflage. They would appear indistinguishable from natural asteroids or comets, emitting no signals, avoiding any behavior that might betray artificial origin. Their mission would not be to communicate but to observe. Such probes could monitor emerging civilizations, tracking signs of technological progress, measuring whether new species might one day pose risks, offer opportunities, or warrant continued surveillance. From this vantage point, the recent increase in interstellar object detections could be interpreted differently. Instead of reflecting natural populations that our improved instruments are only now revealing, perhaps it signals a rise in surveillance activity, triggered by humanity's rapid technological progress over the past century. This is, of course, highly speculative, unsupported by evidence, and perhaps unfalsifiable with today's tools. Yet, as a framework, it forces us to take seriously the possibility that survival, rather than communication, drives the strategies of galactic civilizations. If the dark forest hypothesis captures reality, then the cosmos may be both full and empty, at once crowded with intelligence, yet devoid of overt contact. We may be watched, but not welcomed, observed, but not invited into any wider community of worlds. In such a universe, wisdom might lie in caution, not in paranoia, but in prudence, not in fear, but in the recognition that in a dark forest, the first rule of survival is knowing when silence is the only safe response. August 15th, 1977, 10:16, in the evening Eastern Standard Time. In a quiet office at Ohio State University, Jerry Eman, a volunteer researcher with the Big Ear Radio Telescope's SETI program, was scanning through stacks of computer printouts when something made him pause. On the sheet before him, columns of numbers and letters represented hours of radio observations. Suddenly, one sequence leapt off the page, a spike in radio intensity at 1420.456 MHz, tantalizingly close to the hydrogen line frequency that SETI researchers have long considered a natural choice for interstellar communication. The signal lasted 72 seconds, precisely the duration expected for a fixed-point source drifting across Big Ear's field of view as the telescope rotated. Eman circled the data in red ink and wrote one word in the margin: "Wow." For more than 4 decades, the "wow" signal has lingered as one of astronomy's most enduring enigmas. It came from the direction of Sagittarius, strong, narrowband, and perfectly aligned with what researchers imagined an intentional extraterrestrial transmission might look like. And then it was gone. Follow-up scans of the same sky region produced nothing. Other telescopes found nothing. It never repeated. Over the years, hypotheses have multiplied. Perhaps it was interference from a passing satellite. Perhaps terrestrial transmissions bounced off space debris. Perhaps a comet's hydrogen cloud drifted across the telescope's view. Yet none of these explanations has closed the case. The signal's characteristics remain stubbornly consistent with what one would expect from a deliberate transmission. But consistency is not proof. One data point, no matter how enticing, cannot overturn the principle that extraordinary claims require extraordinary evidence. The WOW signal highlights the central challenge of SETI, separating potential artificial transmissions from the cacophony of natural and human-made radio noise. Earth itself is a noisy planet. Television broadcasts, radar sweeps, satellite communications, even microwave ovens contribute to the fog of signals that fill the spectrum. The cosmos adds its own chorus. Pulsars, quasars, magnetospheres, and hydrogen clouds all radiate naturally. Identifying a genuine artificial signal requires rigorous filtering, careful analysis, and, above all, independent confirmation. A single fleeting spike, however alluring, is never enough. But perhaps the problem is not only in our filters, but in our assumptions. Traditional SETI strategies focus on continuous or periodic signals, steady beacons that broadcast over long periods, easily detectable to anyone listening at the right frequencies. Such transmissions would make sense for civilizations eager to announce themselves. Yet if the galaxy resembles a dark forest, as some theorists suggest, then such broadcasts would be suicidal. Advanced civilizations might instead use burst transmissions, frequency-hopping protocols, or deliberately irregular signals designed to evade unwanted detection. More provocatively, they might camouflage their communications by timing them to coincide with natural events such as the passage of interstellar objects through planetary systems. Imagine a civilization monitoring Earth with hidden probes. When an object like Oumuamua or Borisov drifts through, a probe could transmit a signal masked by the plausible noise of cometary activity. To human astronomers, such emissions would look like natural radio interactions between the solar wind and a comet's coma. In reality, they could be carefully chosen bursts of information, hidden in plain sight. The timeline tempts speculation. Oumuamua in 2017, Borisov in 2019, now 3I Atlas in 2025, 3 interstellar visitors in less than a decade. Could these events correlate with unexplained radio anomalies in our archives? The difficulty lies in the way data have been handled. Radio astronomy surveys are not designed to test the hypothesis of coordinated signals. Most transient detections that fail to repeat are quickly discarded as interference or anomalies outside natural models. Yet these discarded fragments may be precisely where evidence of intentional communication hides. Re-examining historical data with fresh eyes and new tools could yield surprises. Today's signal processing technologies, machine learning algorithms, distributed computing networks, advanced pattern recognition can identify correlations that escaped earlier researchers. Signals once dismissed as noise could reveal structure under closer scrutiny, but such reanalysis faces barriers. Many older telescopes did not preserve raw, high-resolution recordings. Instead, they stored reduced summaries, stripped of the very anomalies that might matter most for SETI. Biases in observational strategies, preferences for particular frequencies or sensitivities may have filtered out unconventional signals altogether. The challenge grows sharper when one considers the possibility of deliberate disguise. A truly advanced civilization could design signals indistinguishable from natural phenomena, exploiting our assumptions as camouflage. A brief burst timed with a comet's outgassing, a narrow spike hidden in the chatter of pulsars, a signal encoded in patterns too subtle for our current instruments, all could slip past unnoticed. The WOW signal remains unique, but perhaps only because it was one of the few times chance and circumstance aligned just right for us to notice. Whether coincidence, interference, or something more, the wow signal continues to whisper across decades, reminding us how fragile and ambiguous the search for other minds can be. It also reminds us that what we dismiss today as noise might, under tomorrow's analysis, reveal itself as a message. In a universe vast enough to hide both stars and civilizations, the line between signal and silence may be thinner than we think. A civilization far beyond our own could, in principle, design radio transmissions that mimic the familiar signatures of nature itself. They might create signals with pulsar-like regularity, quasar-like spectra, or the faint emission patterns of hydrogen clouds. To our instruments, these would look indistinguishable from known astrophysical sources. Detecting the artifice behind such mimicry would demand exquisitely detailed analysis, searching for the faintest inconsistencies, tiny deviations in timing, frequency, or intensity that betray an artificial hand. Yet, the same technological sophistication that makes interstellar communication possible could also allow perfect camouflage, rendering the imitation seamless. Other communication strategies pose similar puzzles. Optical SETI searches for anomalous flashes of light laser pulses that might announce another civilization's presence. But such beams could easily be disguised as stellar flares or the flicker of asteroid reflections. Infrared observations seek the waste heat of technology, but waste heat could be masked as the glow of dust clouds or planetary atmospheres. Even gravitational wave astronomy, the newest frontier, holds possibilities. One can imagine civilizations harnessing black holes for energy or even controlled mergers as a form of communication. But identifying such signals as artificial would require an understanding of gravitational astrophysics far deeper than we possess today. The core difficulty is unsettling. We may be searching for intelligence that does not want to be found. It is like trying to detect soldiers hidden in camouflage who know you are looking for them and have perfected their concealment over centuries. Yet this does not mean the task is hopeless. Each advance in our knowledge of natural astrophysical processes sharpens our ability to spot outliers. Each improvement in signal processing equips us to detect patterns invisible to human eyes, and each expansion in survey coverage increases the likelihood of finding correlations between events across different instruments and wavelengths. The key insight is that we must seek patterns rather than isolated anomalies. A single burst of unexplained radio noise could be anything: a glitch, a passing satellite, or a cosmic coincidence. But multiple anomalies, appearing in connection with interstellar objects, or displaying coordination across radio, optical, infrared, and gravitational channels, might suggest systematic intent. Pursuing this requires rethinking how astronomy handles its data. Instead of segregating observations by discipline, we need integrated approaches that compare signals across the spectrum. Instead of discarding anomalies as useless noise, we must archive and analyze them systematically. Most importantly, we must remain open to surprise. Intelligence, by its nature, is creative, and advanced intelligence may use communication methods that do not resemble anything human scientists have yet imagined. The universe is filled with signals we do not yet recognize. Some will turn out to be natural phenomena, awaiting explanation. Others may be messages, concealed in the static, hidden in plain sight. The next time you hear the hiss of cosmic noise, remember, not all noise is meaningless. Some of it may be the universe whispering, waiting for us to learn how to listen. A bigger pattern emerges threads in the night, weaving themselves into a story larger than any single anomaly. Step back from the puzzle of Oumuamua's strange acceleration, from Borisov's unusual chemistry, from 3I Atlas's uncanny timing. Step back from the arguments between those who cling to natural explanations and those who dare to suggest artificial ones, from the clash of conservative methodology and speculative imagination. When you zoom out, the outlines of something new come into focus. We are witnessing the birth of a new field of astronomy. Before 2017, interstellar objects lived only in theory. They were equations scribbled in papers, simulations run on computers, abstractions that existed to help astronomers test ideas about how planets formed in distant star systems. Researchers could calculate how many such objects might wander between stars, estimate their sizes, and predict how often future telescopes might find them. But they were ghosts, mathematical constructs, not realities. That all changed when Oumuamua appeared. In less than a decade, we have gone from none to 3 confirmed detections. Oumuamua in 2017, Borisov in 2019, 3I Atlas in 2025. 3 visitors in 8 years, with more almost certainly waiting to be found. The transition has been profound, from speculation to observation, from abstract theory to tangible data, from a desert of silence to the beginnings of a crowded conversation. This shift has already forced astronomers to confront how little we knew about interstellar space. Conventional models long suggested it was a sparse void, a vast emptiness where ejected fragments from planetary systems wandered so rarely that detection would be a once-in-a-decade triumph. Yet, the evidence of 3 detections in such a short span challenges those assumptions. Either our surveys have become sensitive far faster than predicted, or interstellar space is more populated than we ever imagined. The Vera C. Rubin Observatory, coming online in 2025, will answer this question with ruthless clarity. Its 8.4-meter mirror and 3.2 gigapixel camera will scan the visible sky every 3 nights, mapping with a sensitivity that dwarfs previous surveys. If interstellar objects are as rare as old models claimed, Rubin should find 1 or 2 per year. If the true population is larger, Rubin could uncover dozens annually. Conservative predictions place the rate at 1 or 2. Optimistic models, assuming higher ejection rates during planetary formation, suggest numbers in the tens. Some analyses, under the most favorable assumptions, even allow for 70 discoveries per year. Such uncertainty reveals our ignorance of planetary birth in other systems. How often do forming worlds sling icy bodies into the interstellar dark? How many fragments escape their parent stars altogether during planetary migrations? How long do they endure, wandering among the stars before collisions grind them down, or stellar flybys disrupt them? Each answer alters the predicted population dramatically, and Rubin's data will finally provide the statistics needed to decide. But statistics alone may not tell the whole story. There is another possibility, one that sounds like science fiction but has serious advocates. What if some of these interstellar visitors are not natural wanderers at all, but technological artifacts? The thought is provocative, but it also carries testable implications. First, timing. 3 detections in 8 years could simply be chance. But it might also reflect increased activity, civilizations becoming more ambitious, sending more probes, expanding their surveys as they mature. Second, diversity. Oumuamua, Borisov, and 3I Atlas each look radically different, elongated, icy, comet-like. Natural populations might show more uniformity, shaped by the same physical laws of ejection and survival. Their diversity could signal design. Third, the geometries of approach. While natural ejections should scatter randomly, systematic approaches, clustered timings, or consistent alignments might hint at intent. We stand at the threshold of discovery. Threads in the night are beginning to weave themselves into a tapestry. Whether the pattern reveals the hidden dynamics of planetary formation or the fingerprints of intelligence older and stranger than ours remains unknown. But what is certain is that interstellar visitors have transformed from theory into reality, and the story they carry is only beginning to unfold. Truly random interstellar objects should drift into our solar system from every direction with equal likelihood. Yet the small sample we have collected hints at something more structured. Both Oumuamua and 3I Atlas approached from the general direction of the galactic center. Statistically, with so few data points, the significance of this clustering remains uncertain. It may mean nothing at all. Still, such patterns remind us that we must remain vigilant, designing surveys not only to study natural interstellar debris, but also to test, however cautiously, the possibility that some arrivals might be artificial. At present, most observational programs focus on parameters that illuminate planetary formation, size, shape, rotation, outgassing patterns, and chemical composition. These data are crucial, offering insight into how distant star systems evolve. But a different layer of questions lingers. What about radio emissions that could suggest internal power sources? Infrared signatures that reveal unexpected heat production? Trajectories altered in ways inconsistent with natural gravitational or thermal forces? Searching for such anomalies would not prove artificiality. Advanced civilizations could engineer probes so carefully that they appear indistinguishable from nature. Still, systematic searches would generate data that current methods neglect, bringing us closer to testing possibilities rather than ignoring them. The implications of these inquiries stretch far beyond the mysteries of individual objects. If interstellar space is more populated than models predicted, whether with natural debris or artificial constructs, the galaxy may be far more integrated than conventional astronomy assumes. Natural interstellar comets and asteroids function as messengers, carrying molecular information between systems, spreading heavy elements forged in ancient stars and enriching the galactic medium over geological timescales. A dense population of such wanderers would accelerate this chemical mixing, potentially seeding more planets with the ingredients of life. Artificial interstellar objects, however, would signal something altogether different. They would imply that intelligence has transcended the boundaries of its home stars, creating webs of observation and exploration that span dozens or even hundreds of systems. Such a network might persist for millions of years, recording the births and deaths of worlds, cataloging the rise and fall of species, quietly monitoring the galaxy without ever announcing itself. This perspective reshapes even the famous Drake equation. Traditionally, the equation asks how many civilizations in our galaxy might be communicating through radio signals. But what if that is the wrong question? Perhaps the real question is how many civilizations are actively exploring, deploying probes, and gathering information. Exploration and communication are not the same. Communication exposes you to risk. Exploration can be done silently. A civilization concerned with survival might choose the latter, consistent with the dark forest hypothesis. In such a galaxy, intelligence might be common yet hidden, detectable only by recognizing faint signatures of artificiality disguised as natural phenomena. To test such ideas, we need both technological and conceptual advances. We require instruments capable of detecting faint, fast-moving objects with higher precision. We require sophisticated processing techniques to mine vast datasets for patterns too subtle for earlier methods. And we require new theoretical frameworks that allow us to weigh natural and artificial explanations with rigor rather than bias. Above all, we must remain scientifically disciplined without closing ourselves off to radical possibilities. Extraordinary claims demand extraordinary evidence, but they also demand extraordinary effort. We cannot know whether the evidence exists unless we dare to search for it. The coming decade promises to be transformative. The Vera C. Rubin Observatory will multiply detection rates by orders of magnitude. Space-based telescopes will provide sensitivity across electromagnetic bands never before harnessed in concert. Advances in data processing will uncover correlations invisible today. These revelations may confirm that interstellar visitors are nothing more than planetary debris flung across the stars. Or they may hint at something more profound: networks of intelligence that have been operating for ages, just beyond the limits of our perception. Either way, the discoveries will redefine our understanding of our place in the cosmos. For the first time, we are no longer alone in speculating about our solitude. The universe has sent us visitors, and we are finally learning to recognize them. The deeper question now is whether every one of those visitors is natural, or whether some may be carrying with them more than chemical stories, fragments of a network that recycles not only matter, but perhaps intelligence itself. Science versus speculation, firelight and shadows. Science advances through a delicate interplay between boldness and restraint. Bold hypotheses open new frontiers, while careful skepticism ensures that discovery remains tethered to reality. Too much boldness untethered from evidence drifts into fantasy. Too much skepticism risks freezing progress, leaving genuine mysteries unexplored. The debate over interstellar visitors embodies this tension with striking clarity. On one side stands the mainstream astronomical community, seasoned by centuries of separating cosmic signals from cosmic noise. Their arguments are cautious, evidence-driven, and anchored in the principle that extraordinary claims demand extraordinary proof. 3. Atlas, they insist, is precisely what it seems to be: a comet from another star system. Hubble Space Telescope images confirm its dusty coma and luminous tail, unmistakable signs of sublimating ices. Its orbit aligns with gravitational expectations, tracing the hyperbolic path of an object flung from its home system long ago. Its inbound speed of about 58 kilometers per second fits comfortably within predictions for natural interstellar debris. NASA's analyses assure us that it poses no danger, will loop around the Sun near October 30th, 2025, and will pass Earth at a safe distance of roughly 1.6 astronomical units. Even Oumuamua, once hailed as astronomy's great anomaly, has been gradually reconciled with natural explanations. In 2023, Jennifer Bergner and Daryl Seligman published a model showing how cosmic rays could split water molecules in ice over millions of years, trapping hydrogen that later vented as the object warmed. This invisible hydrogen outgassing, they argued, produced the slight but puzzling acceleration Oumuamua exhibited. The explanation relies on known physics, accounts for observed properties, and requires no speculative leaps into alien engineering. Borisov, by contrast, presented no puzzles at all. It looked and behaved like a comet, producing a coma and tail exactly as expected. Its elevated carbon monoxide levels pointed to formation in a colder region than our solar system, providing valuable insight into planetary chemistry across the galaxy. For the mainstream, the pattern is clear. Natural explanations have consistently explained the data, and each explanation leads to testable predictions. The hydrogen model for Oumuamua, for example, makes forecasts about how similar objects should behave, predictions that future observations can confirm or refute. Invoking artificial explanations without strong evidence, mainstream astronomers warn, risks turning astronomy into speculation untethered from testability. History offers cautionary tales. Pulsars were first suspected to be alien beacons. They turned out to be rotating neutron stars, exotic and astonishing in their own right. Gamma-ray bursts once fueled speculation about extraterrestrial wars. They proved to be hyper-energetic stellar explosions visible across billions of light-years. Fast radio bursts, too, once baffling, are now linked to magnetars and other astrophysical sources. Again and again, patient investigation has shown nature to be stranger and more beautiful than our speculative imaginations. Yet across the firelight, another voice speaks. Avi Loeb and colleagues argue that conservatism, however methodologically sound, has created a blind spot. If technological artifacts exist among interstellar visitors, the current frameworks of astronomy would never reveal them. Observational programs are built to study natural properties, size, mass, chemistry, not artificial ones. Data processing systems are optimized to filter anomalies, not preserve them. Theoretical models assume nature, not technology. The consequence, Loeb contends, is a systematic failure to even test artificial hypotheses. It is not that natural explanations are implausible, but that alternative interpretations remain unexamined. How can one know nature suffices if one never tests the possibility of technology? The Galileo project, launched in 2021, aims to correct this imbalance. Its philosophy is conventional: design instruments, gather data, analyze results, and publish findings. What distinguishes it is the research target technological signatures. Instead of filtering out anomalies, it collects them. Instead of assuming natural causes, it leaves the question open. In this sense, the project is less a departure from science than an extension of its spirit, applying the same rigor to possibilities the mainstream community has long regarded as taboo. Thus the debate continues, lit like shadows against firelight. On one side, cautious empiricism; on the other, provocative openness. Both are necessary. The future of interstellar astronomy will depend not only on sharper instruments and better surveys, but also on our willingness to balance skepticism with imagination. In that balance lies the difference between dismissing anomalies as noise and recognizing them as the first whispers of something extraordinary. The controversy surrounding some of Avi Loeb's more specific claims, particularly the suggestion that fragments of an interstellar meteor retrieved from the Pacific Ocean might represent artificial material, highlights both the difficulties and the importance of pursuing such questions. Initial analyses reported tiny metallic spherules that, Loeb argued, might not fit comfortably within terrestrial explanations. Some researchers suggested they could instead represent interstellar debris of natural origin. Others argued that the material could be explained by more ordinary terrestrial processes. The dispute is precisely what the scientific method demands when faced with extraordinary claims: competing hypotheses, careful analysis, independent verification, and attempts at replication. What is remarkable is not that the claims are disputed, this is entirely normal, but that they are being investigated systematically rather than dismissed outright. Yet the debate over Loeb's claims opens into broader questions about the place of speculation in science. How much deviation from established thinking should the scientific community tolerate? At what point does healthy skepticism harden into a conservatism that blinds us to discovery? Conversely, at what point does bold speculation cross the line into unfounded conjecture that damages scientific credibility? These questions are not abstract. They cut to the heart of how science should proceed when the stakes could not be higher. If interstellar visitors include artificial artifacts, and if we overlook this possibility because of methodological rigidity, we risk missing evidence of extraterrestrial intelligence, arguably the most consequential discovery humanity could ever make. The risk of false negatives failing to recognize artificial signatures because they do not fit into established frameworks may in fact be greater than the risk of false positives, But false positives carry their own weight. Declaring evidence of extraterrestrial intelligence prematurely could undermine public trust in science, distort media coverage, and divert attention from more fruitful avenues of research. The balance between these risks depends heavily on how likely we think extraterrestrial intelligence and interstellar exploration truly are. If such phenomena are extraordinarily rare, then prioritizing caution and minimizing false positives is wise. If they are reasonably likely, then minimizing false negatives, actively searching for artificial signatures, even when natural explanations suffice, becomes equally important. Estimating these probabilities brings us back to questions embedded in the Drake equation. How common are habitable planets? How often does life arise? How frequently does intelligence evolve? And how likely is it that intelligence develops interstellar technologies that might leave detectable traces? These questions remain unresolved. Discoveries in exoplanet astronomy have tilted the scales toward optimism in at least one area. Planets similar to Earth appear common. Data from Kepler and other missions suggest that as many as 20% of Sun-like stars host potentially habitable planets. If life emerges readily and intelligence often follows, the galaxy could be home to millions of civilizations. Yet each step in the chain carries uncertainties so large that both extremes from we are entirely alone to we live in a galaxy, swarming with intelligent species remain plausible. This deep uncertainty leaves space for both conservative and speculative approaches. The conservative stance emphasizes minimizing false positives, demanding extraordinary evidence before entertaining artificial explanations. The speculative stance emphasizes minimizing false negatives, arguing that we must actively search for technological signatures, even if natural explanations suffice. Both approaches are scientifically valid, and both contribute to progress. They are not mutually exclusive, but complementary, addressing different facets of the same problem. The central question is not which approach is correct, but how to balance them given the extraordinary stakes. The coming decade promises to sharpen this debate. With the Vera C. Rubin Observatory set to revolutionize sky surveys, the number of detected interstellar objects will grow dramatically. Patterns invisible in our current tiny sample may soon emerge. If all newly discovered objects behave exactly as cometary physics predicts, the case for purely natural origins will strengthen. If even a few display anomalies that resist conventional explanations, the case for broader, more speculative inquiry will become impossible to ignore. Until then, the tension between skepticism and speculation serves its purpose. It ensures that science neither rushes blindly into sensational claims nor turns its back on mysteries that could hold profound significance. Both camps share a commitment to evidence. They differ only in how much evidence they require before exploring possibilities that challenge orthodoxy. Science, like exploration, is never free of risk. Be too cautious, and discoveries may slip by unnoticed. Be too bold and credibility may be lost. The challenge and the art is to strike the right balance. When the question at stake is whether we are alone in the universe, perhaps both caution and boldness deserve their place by the firelight of discovery. Who is the exhibit, and who is the observer? The answer may depend on which future we find ourselves in. From the same data, Oumuamua's elongated mystery, Borisov's chemical signature, 3I Atlas's cometary halo, two radically different interpretations emerge, each painting a distinct portrait of humanity's place in the cosmos. Future one begins with the natural explanation. In this vision, every interstellar visitor we encounter is a fragment of ordinary debris, ejected during the turbulent formation of distant star systems. Oumuamua, Borisov, 3I Atlas, and the countless others that the Vera C. Rubin Observatory will soon reveal our cosmic messengers, their significance not in exotic origins but in what they carry, the chemistry of other suns and their planets. Here, the galaxy functions as a recycling program on a grand scale. Comets and asteroids are scattered like seeds, drifting for millions or billions of years until they pass through another star's domain, offering astronomers a rare glimpse of planetary processes otherwise hidden across light years. The implications are profound, even if the objects themselves are unremarkable. Each one encodes conditions in its birth system, the thermal gradients in its protoplanetary disk, the abundance of elements available for worlds to form, the efficiency of ice condensation in its outer reaches. Borisov's enrichment in carbon monoxide already hinted at colder formation conditions than those in our own solar system. Future visitors will broaden this chemical census, mapping the diversity of planetary nurseries and answering whether Earth-like planets are the products of rare alignments or the natural outcome of many different stellar environments. Statistics will matter as much as specifics. If Rubin finds hundreds of such wanderers each year, then interstellar space is not empty but crowded with emissaries, a galactic ecosystem in which matter flows constantly between stars. Such traffic would reshape astrobiology. Panspermia, the idea that microorganisms might hitchhike between worlds, would move from speculation to likelihood if carriers are abundant. Even without biology, these objects serve as chemical bridges, distributing heavy elements forged in ancient stars more evenly throughout the galaxy. Over cosmic time, this would make Earth-like worlds more probable around a wider range of stars. From this angle, humanity itself becomes a product of galactic circulation. The calcium in our bones, the iron in our blood, the carbon in our DNA. Perhaps these atoms crossed interstellar distances many times before settling into the nebula that birthed our Sunday. We are not isolated. We are citizens of a galaxy that has been mixing and remixing its ingredients for billions of years. Our story is written not only in the solar system, but in the exchange of matter across neighborhoods we will never visit. Future 2 tells a different tale. Here, some interstellar visitors are not mere comets but artificial artifacts, probes launched by civilizations far older and more advanced than our own. In this scenario, humanity has lived under quiet observation for centuries, perhaps millennia. Every leap in human history, the taming of fire, the invention of agriculture, the rise of cities, the Industrial Revolution, the nuclear age, the dawn of spaceflight would have been monitored and recorded. Our triumphs and failures would be entries in a catalogue of civilizations, a record kept by minds that have seen these stories unfold many times before. From such a perspective, we are adolescents on the cosmic stage. We have built powerful technologies, yet struggle to wield them responsibly. Nuclear weapons, climate disruption, mass extinctions, social divisions, these crises that dominate our politics may appear as familiar patterns to alien observers, milestones in the dangerous passage from primitive survival to mature stewardship. Our species becomes not an exception but a case study, one more data point in a long galactic experiment, tracking whether intelligence learns to survive its own inventions. The same evidence, the same visitors, lead us toward two very different futures. In one, we are part of a galaxy-wide exchange of matter, our lives shaped by the slow chemistry of stars. In the other, we are subjects under observation, our history watched by intelligences whose patience stretches across millennia. Which story is true remains uncertain. For now, we stand both as observers and as exhibits, staring into the dark forest of the cosmos, unsure of who might be watching from the shadows. Whether humanity successfully navigates the immense challenges before us or collapses beneath their weight may determine our long-term relationship with whatever galactic civilization might exist. Species that manage to live sustainably within their planetary limits could earn entry into a wider cosmic community. Those that destroy their environments or themselves might become cautionary tales, examples studied by future emerging civilizations as warnings of what not to do. The observation hypothesis sharpens these questions by placing us in an uncomfortable position. If we are being studied like wildlife in a preserve, what ethical obligations fall upon the observers? Do they have the right or even the responsibility to intervene if we stagger towards self-destruction? Should they help us overcome problems they themselves solved long ago? Or are we being observed precisely because non-interference allows natural selection to function at the level of civilizations, filtering out those unable to handle technological adolescence? Perhaps the galaxy is rich with intelligence, not in spite of the difficulties that young civilizations face, but because those difficulties serve as evolutionary gates, ensuring that only the wise and sustainable endure. From this perspective, first contact may be postponed until humanity demonstrates the ability to handle planetary-scale technologies without catastrophe. Observers might be waiting for us to resolve climate change, dismantle nuclear arsenals, stabilize population levels, and develop cooperative frameworks for managing resources. Graduation from observed to observer status would presumably depend on criteria rooted in the values and survival strategies of civilizations that have already succeeded. Those who remain trapped in zero-sum competition, who see other intelligences only as threats, may never be invited into broader galactic affairs. But such a hypothesis also strikes at human dignity and agency. Are we truly free to chart our own future, or are we actors on a stage, repeating a script that countless civilizations have performed before us? The answer may depend on whether the observers follow something like the prime directive of science fiction, abstaining from interference in developing worlds, or whether they sometimes offer subtle nudges to promising species. Either way, the knowledge of being watched would fundamentally alter human psychology. The existential loneliness that has defined our worldview since the Copernican revolution would give way to existential anxiety. We are not alone, but under judgment by beings whose standards we cannot fathom. Both possible futures, natural or artificial, carry profound implications for our development. If interstellar visitors are natural, they remain treasures of discovery. Each one offers direct evidence of planetary formation in alien systems, samples of chemistry and physics written across the galaxy. To pursue this opportunity, we should invest in the tools to study them more fully. Next generation telescopes, faster spacecraft capable of interception, and advanced analytical techniques. Practical implications also follow. If interstellar space teems with wandering debris, human voyages to other star systems will need to account for collision hazards far greater than current models assume. If some visitors are artificial, the stakes rise higher still. We must develop the ability to distinguish natural from artificial origins with rigor, while carefully planning how we might respond if evidence of extraterrestrial technology emerges. Existing contact protocols, designed in the Cold War era, assume distant radio conversations between civilizations separated by light years. But if advanced societies routinely seed other systems with observation probes, first contact may be immediate and local. Our response could define our trajectory for millennia. Paranoia or aggression might confirm suspicions that we are not ready. Cautious openness might signal that we have matured enough to balance self-protection with cooperation. Most importantly, both futures compel us to expand our perspective. Whether the galaxy is filled only with natural wanderers or partly with intelligent observers, our destiny is bound to cosmic processes operating on scales far beyond a single world or a single age. We are not merely residents of Earth orbiting an ordinary star. We are participants in a galactic ecosystem whose full scope is just beginning to reveal itself. The central question is no longer whether that ecosystem is entirely natural or partly artificial. The question is whether humanity can grow into a species capable of contributing responsibly to whatever reality awaits us among the stars. Return with me to that image from the beginning. Silent travelers gliding through the faint glow of zodiacal light while most of us sleep, unaware that our solar system has become a crossroads for objects born in distant star systems. In the weeks since this narrative began, 3-1 Atlas has completed its dramatic passage. October 30th, 2025, the day of closest approach, came and went. Like a stone hurled in a cosmic sling, the object curved around the sun, accelerated by gravity, and continued on its path back into the interstellar night. Worldwide, telescopes followed its trajectory with patient precision. Spectroscopes separated its light into spectra, revealing hints of the gases released as its ices sublimated in the sun's heat. Radio dishes scanned the skies, listening for signals that might distinguish this visitor from mere cometary debris. The data is now archived, awaiting years of analysis, the careful work of astronomers who turn faint traces of light and radio into scientific conclusions. The most likely outcome, of course, is confirmation of the mainstream interpretation. 3I Atlas is a natural interstellar comet, a mixture of ice and rock shaped by the familiar physics of outgassing and orbital mechanics. Another entry in the growing catalogue of extrasolar debris, useful for science, but not revolutionary. Yet the larger question persists, haunting every new detection. How many of these objects have passed unnoticed through our skies before our instruments were capable of seeing them? How many are out there now, slipping silently through the vast expanse of our solar neighborhood, destined to be discovered in coming years? The Vera C. Rubin Observatory has finally opened a new chapter in answering those questions. Its enormous mirror and gigapixel-scale camera are mapping the southern sky with unmatched sensitivity, capturing the motion of faint wanderers that would once have gone unseen. Early results suggest that interstellar visitors are indeed more common than astronomers believed before 2017. Not overwhelmingly more common, but enough to overturn the image of interstellar space as a nearly empty desert. Each new detection contributes to a galactic census. The objects arrive from many directions, consistent with a broadly uniform distribution of debris in our local stellar region. Their compositions vary, carrying signatures of the different environments where they first condensed. Their velocities match the predictions of models describing the ejection of comets during planetary formation. The growing dataset reinforces the view that we are witnessing the visible edge of a vast and ancient population, a traffic flow of cosmic fragments long hidden from us by the limits of our instruments. Rubin is now doing for interstellar debris what Hubble once did for galaxies, showing us that what seemed sparse and quiet is in fact crowded and dynamic. But patterns can deceive, especially when drawn from small samples and partial information. Oumuamua remains the reminder of that caution. Its anomalous acceleration tiny, yet measurable, forced astronomers to wrestle with explanations. The hydrogen outgassing model proposed in 2023 convinced many that the mystery was resolved. Yet the explanation rests on assumptions that cannot be tested now that Oumuamua has vanished beyond reach. Its internal structure, its exposure to cosmic rays, its porosity, these details are lost forever, leaving us with plausible models but no certainty. The object remains a riddle we can no longer touch. In contrast, Borisov was almost a comfort. Its behavior was textbook cometry, complete with coma, tail, and predictable outgassing patterns. Yet even Borisov surprised us with its striking carbon monoxide enrichment, a chemical fingerprint suggesting formation in a far colder environment than that of most solar system comets. The lesson was clear. Even ordinary, seeming visitors can carry extraordinary insights about the diversity of planetary nurseries. 3I Atlas, like Borisov, largely conforms to expectations, while also leaving room for mystery. Its outgassing patterns match those of known comets, but its precise size remains uncertain, somewhere between a few hundred meters and several kilometers. Its composition awaits deeper spectroscopic study. Its rotation period and internal architecture remain unknown. It appears natural, yet still holds secrets that will take years of careful work to decode. In this interplay between anomaly and explanation lies the essence of science. Each visitor brings us closer to understanding the true structure of the galaxy, yet each one also reminds us of how much remains hidden. Whether wholly natural or carrying traces of something more, these wanderers compel us to look outward with sharper eyes, to treat every glimmer in the night sky as a potential messenger from worlds we will never see. These uncertainties highlight the fundamental difficulty of studying objects that enter our solar system only once, racing past at high velocities and offering fleeting observational windows. We are, in effect, attempting to reconstruct alien worlds and distant processes from snapshots taken at vast distances. It is like trying to understand the complexity of human civilization by watching a few cars pass on a highway miles away. The analogy leads to an unsettling possibility. What if some of those cars are not empty, but contain passengers observing us as carefully as we are observing them? This idea remains speculative, unsupported by hard evidence, and perhaps impossible to test with current or even foreseeable technology. Yet it offers a framework that stretches beyond the traditional search for extraterrestrial intelligence, which has long focused on detecting radio transmissions from civilizations separated by light years. If advanced civilizations exist, and if they have developed technologies for interstellar travel or surveillance, then it is plausible that our solar system is already under observation by robotic probes. Such devices might be designed to remain inconspicuous for millennia, hiding among the natural debris of comets and asteroids, while recording the progress of potentially intelligent species. From this perspective, the recent surge in detections of interstellar objects might take on an entirely new meaning. Instead of simply revealing a population of natural wanderers that our telescopes have only now become sensitive enough to detect, these discoveries could represent an uptick in deliberate surveillance activity. Humanity's technological leap in the last century, radio broadcasts, nuclear weapons, space exploration may have triggered greater attention from hypothetical watchers monitoring for precisely such milestones. The difficulty, of course, is that such a hypothesis may never be provable. A sufficiently advanced civilization would design its probes to mimic natural phenomena so effectively that even our most sophisticated instruments would be unable to distinguish them. Outgassing could be simulated, trajectories carefully calculated, surfaces engineered to look like inert rock and ice. Even if one passed directly by Earth, we might never recognize it for what it was. Still, the speculation serves an important intellectual role. It broadens our sense of the possible in a universe where intelligence may not be rare, but simply quiet and cautious. If humanity is being observed, then every war, every scientific breakthrough, every cultural flowering, and every environmental crisis has been witnessed by non-human intelligence. That thought is humbling. It strips away the assumption that humanity occupies the central stage of the cosmos. But it is also inspiring, suggesting that intelligence has spread across the galaxy in ways systematic, enduring, and immensely more advanced than anything we can currently imagine. Whether that hypothetical network of observers would ever welcome us remains unclear. Perhaps we are being tested against criteria we cannot yet perceive, our long-term survival and cooperative capacity under evaluation. Perhaps observers merely catalog diversity, with no intention of initiating contact. Or perhaps no one is watching at all, and the universe is just as silent and empty of intelligence as decades of radio silence have implied. Both outcomes, observation or isolation, carry immense implications. If we are under observation, then humanity's future may depend on demonstrating maturity, proving that we can manage planetary-scale technology responsibly, and act as potential participants in a larger community. If we are alone, then the responsibility is even greater. We would represent the galaxy's first and perhaps only technological civilization, tasked with carrying the flame of intelligence into the wider cosmos. In either case, the discoveries of interstellar visitors force us to think on scales far beyond the terrestrial. The night sky that once seemed static now reveals itself as a galactic highway, populated with travelers whose journeys began around distant suns. Whether these objects bring only chemical records of alien planetary systems or carry instruments designed to study us, they are our first tangible connections with the wider galaxy. Each visitor offers a choice. We can treat them as purely natural phenomena, valuable for advancing our understanding of planetary formation. Or we can also remain open to the possibility that some may be something more, evidence that consciousness itself has learned to travel the stars. That choice will shape not only our scientific methods, but also our philosophy of existence. So sleep well, but keep one eye on the sky. For in a universe full of wandering messengers, we may not be as alone as we seem.